So the talk I have today is MySQL for Frappe Devs, and yeah, the screen is recording for 10th time. Yes, it is all working. Hopefully now, we'll see if it doesn't work. The talk title is MySQL for Frappe Devs, but it is mostly MySQL for anyone. The Frappe Devs is just uh, like extra information so that I can cut down few things that I would otherwise not cut. And all of you are either brave or you have not checked the schedule. It is 2 hours long, and it was somewhat misleading because it's labeled as workshop. It is pretty much like a lecture, and uh, I mean, when we did it last time internally, it was useful, but at the same time, it is somewhat overwhelming. Like I don't think people have 2 hours of attention span. So, but like the thing is, if you don't get it, go and watch the recordings later or watch the slides later and like explore what you want to. Because I'll start by first giving credits. This is not my creation at all. I'm not a college professor. This guy is. Not this guy, the guy behind him. So that's Andy Pavlo. He runs this class at CMU. CMU is like the rank 1 university in the world. And their DB class is also pretty popular. So they teach this class for a semester-long class. I can't convince people to go through semester-long class, so I condense it down to 3-4 hours, and then I condense it down again to 2 hours today. Hopefully it will be completed in 2 hours. But basically, it's this stripped-down version of the CMU's class, and he puts it out for free. There are videos from every year, and this guy is fucking awesome. And I'm cursing because he also curses in the classes, so it's okay. And yeah, the guy in front is a DJ in the class. They start the class with some, because he likes that kind of hip hop music. Anyway, I'm not into hip hop. I'm not going to do it. But yeah, 100% credit to this guy. Majority of the slides, majority of the content comes from there. I did not create this. Okay, so obviously the class is about learning how to build databases yourself, which is database implementation. How many of you have had any database class in college? Any database class? Okay, almost half. And how many of you did not go to college at all or something? Safwan, okay. And how many of you had database implementation class, which is not the same thing as like learning to write SQL or schema design or all of the relationship algebra. I mean database implementation, which means how the database work internally, like buffer pool. Like, have you heard these terms? What is buffer pool? Can a show of hand? How many of you understand what buffer pool is? 2-3 people. Okay, 4 people. And how many of you understand like how query execution works? Things like that. Okay, still few people. Cool. So you'll get something out of it mostly. Like as far as I know, like most colleges in India do not have DB implementation class for some reason. They only have DB usage and schema, that sort of thing. Some of them do. If you went to IIT or something, you do. But then I don't know what you'll be doing here. So just a warning, because again, it's going to be short talk. I cannot, most DB users operate at this level of where they are just conceptually understanding how DB works. For them, it is a black box where you give declarative queries and you get the results back. They don't understand how it works at all. This is how most of us start. Like, this is how I started. Obviously, no one knows how DB works by default, because it makes no sense to learn that before you learn to write SQL. So most of us are comfortable writing SQL. That I have to assume, because otherwise it's going to be very, very annoying. Then there are developers who write these databases. These are people who are systems programmer who write low-level code like C, in C, C++, etc., or Rust in these days. So that is very low-level implementation detail where you care about how it is laid out in memory, and a lot of low-level details that obviously I cannot cover here. So we want to mostly just stay at high level, discuss things at high level. But this session still assumes that you know basics of C, basics of how operating systems work. Just bare bone basics, and I'll cover wherever I can't, wherever there is some doubt, but obviously I can't cover all the prerequisites here. So a lot of hand-wavy things, I'll have to deliberately be somewhat hand-wavy, because if I go into too many details, I'll not complete anything. So just a warning, you can anyways go and get the detailed actual explanations for these things. So this is roughly the outline. The whole session is split into 6 parts. The last part is very small. First 5 of them are very important. They cover individual things like storage is how data is stored, buffer pool is how data is read and processed, indexing is how you speed up reading of data and processing of data, query planner and execution is how you take declarative things and convert it into some actual execution. Concurrency locking is how you allow multiple users to do the same thing. So all of this is important, and knowing all of this helps you debug things better, help you design things better, help you improve performance. This basically lets you go beyond the insight where you just can read the query and decide index, oh, I'll add this index and see if it works or not. This gives you much better insight. Like understanding all of these things gives you much better insight, and like without even trying things, you can tell confidently what is wrong and what can be attempted to fix things. So this is the outline. Basically, after just some modalities for the talk, I'll have to do most of the individual things non-stop, but after all of them, I'll pause and take questions. If we don't have enough time for questions, find me after the session or anywhere. And you can find the slides on my site. They have been there for 2 years now. This is a rehash of the talk we did internally at Frappe. So everything okay? Okay. So with that, I'll start with storage. So databases store a lot of data. Like we have gigabytes to terabytes of data. And these are the latency numbers. So these are the things that you should know roughly. You don't need to remember them, but you should know roughly what is latency of reading something from RAM versus what is latency of reading something from SSD versus traditional hard disk. Like these are rare now, but roughly 100 millisecond is the 100 nanosecond is the time it takes to read something from RAM. 16,000 nanosecond is SSD. Now, usually people can't appreciate this because nanoseconds we can't picture. So you just normalize it to what would it sound like if it was in seconds. So if it was going to take some 1 second to read something from RAM, it would take 2.6 minutes. So it is like order of magnitude, like 2 or 3 order of magnitude bigger. So you can't rely on SSDs. Even though SSDs are fast, they are not as fast as RAMs. So the whole point of designing databases is you smartly utilize the available RAM, and you might have a database that does not fit in RAM, but you smartly utilize the RAM so that you have very fast access. And this job, this whole thing is managed by buffer pool, but we'll get into that later. This is again the core idea of how databases work, the disk-oriented databases. This is not memory-oriented databases like Redis, which are completely living in RAM, so they don't have to worry about this. So in general, you'll have memory which is smaller than the database size. If you have a memory that is bigger than database size, you are wasting memory mostly. You should not be. So again, something to learn from this is like if you have a Frappe Cloud server with 32 GB and you are storing 1 GB of database on it, you are wasting 31 GB of it. You don't need that much RAM. You need as much, we'll come to how to estimate the required RAM, but in general, the database size should be bigger than the RAM size. And the job of database is to smartly bring things out from database to RAM and from RAM to database. And we'll discuss what these things are. To do this, databases mostly chop your data into what is called pages. So when you insert a row, several of those rows are clubbed together and created, bunched into like a single page. And the pages, if you know how disk, how many of you know how disks work, like SSD or hard disk? Like just roughly how they work. Like how will you read? 1 or 2 people, okay. So you understand binary, right, at least? So everything you store everything you write to a disk is just converted to zeros and ones and with some structure stored into disk. And so disk you do not read or write 1 bit or byte or anything. You usually read or write entire pages, which is roughly, typically 4 KB on disk. You read entire 4 KB of chunk and you write entire 4 KB of chunk when you read or write from disk, because 1 bit and byte is inefficient. So the same thing is done in most databases also. MySQL is exception where it does not follow the typical disk size, disk page size. It uses 16 KB, so it groups together roughly 4 disk pages. Again, this is all roughly because there are disks that have different page size and there are databases that have different page sizes. That's just implementation detail, does not matter. So MySQL typically, or MariaDB typically has 16 kilobyte of page size, and each page has rows like this. Tuple is an academic term for row. Means the same thing, but again, mathematical term, so they use tuple instead of rows. So each page has several rows, and it has some header which tells what exists here, like which table is this, from where, like the range of rows that exist here, so that the database can figure out where to find the rows in this. Uh, this is one page. If you can picture like imagine you have 4 GB of buffer pool, 4 GB of RAM, and each page is 16 KB. Okay, let's for simplification, each page is 4 KB. You divide 4 GB by 4 KB, you have roughly million pages. So there are a lot of pages, and a lot of them need to be managed somehow. So like you might have pages, but you don't want to just throw pages randomly on disk, right? You want to be able to find them out somehow. So this is where like in MySQL stores it by index, and you don't need to know these terms. Like InnoDB is the database engine. It's just like you can picture how MySQL stores. InnoDB and MySQL for most practical purposes are same. Uh, that is the default storage engine. So InnoDB stores things in index. So if you know in Frappe framework, name is the primary index, right? So we'll create like a tree structure of sort, and this is index. We'll explain index later, but you still need to know at least roughly how it is stored. So by primary index, you store the pages, and you can picture like A, B, C, D. They are all sorted by name, and A rows are present in one page. B rows are present in another page, and you can have overlap also, but roughly they are sorted. So like this last leaf nodes contain data, and they are sorted. They are usually sorted. They are sorted by primary key. That is the index. So this is the default storage layout. Now, you also need to know how the individual rows are stored inside the page. So if you picture like a very small example of a table where you have 4 fields, a primary key, timestamp, 2 characters, and integer. Now, when you store this, like there's no such thing as dictionary or objects in databases or memory. Like everything gets flattened out somehow into binary. So, and most modern machines are 64 bits. That is where the word comes from. So you try to pack things into one word and as efficiently as possible. So ID is a primary key, which is integers are 32-bit by default, unless you pick larger ones. So it is using half of the 64-bit word. Then the next thing is, because it is using entire 64-bit word, they are not packing it too tightly, because then reading something half here, half there is harder. So they are just wasting half of the word here and storing it in the next. So this is something, this is called padding usually. But essentially, whatever rows you have, whatever columns you have in a row, they are all flattened and stored in this fashion. And this will again come up if you go and sit through DuckDB talk. Like there are different kind of databases that don't do this. This is row-oriented database. There are column-oriented databases also. So rows ones are optimized for a single record, because again, when you read one sales invoice, you usually care about one row of sales and a row of sales invoice. So this is how they are stored, and yeah, they are not as. It is not as clear, as simple as flattening everything and putting it into one row. Also, can you guess why? Like what kind of data types you cannot just store like this, like in a row? Images you can't store. Text, why can't you store text like this? It makes the row. Yeah, it makes the row bigger, and also it makes the row, what is the row length or row width, rather unpredictable. So you'll have to store pack random amount of things, and then you don't know what is the maximum amount of, what is the maximum size of each row. So usually they do not store the variable things, variable length things, like varchar is a variable length thing, inside the same row. And again, there are optimizations and weird implementation details, but more or less, like the numbers are stored in line, because they are just 32-bit or 64 bits. That is same as how C works, just converted into binary and stored like we saw. varchar is like a number encoded with the length. Sorry, your string encoded with the length of it. So you first store how long the character the string is, and then you store the characters. Now varchar is weird in MySQL because like if you store up to like some 255 bytes, then it will store inside. But if it is longer, then it will not store inside the row. It will store somewhere else and just point it. I'll show example of that. But all other data types, you'll need to understand how those data types work. But more or less, date times are stored as integers like month, date, year. You store all three of them together, and MySQL knows how to read and pass it. Text is, like you said, stored somewhere else. You don't store it in the row itself, because text can be like up to a gigabyte, and long text can be up to a 4 gigabyte or something. So it's really huge amount of data that you are allowed to store. So you can't store it in the row. So you store it somewhere else, and then you point to it with using the concept of pointers from C. Other things don't matter as much. You can read the different data types and the representation, but knowing how these are represented and what these are is still important. So if you don't get it right now, just try and do it later. Again, a lot of this talk is just going to be teaser about things, because I can't go into too many details here. But there is a blog, nice blog by Joel Spolsky called What Every Developer Should Know About UTF-8. So you should go and read that one. Text is not stored in line. Text is stored like this, where you have other 4 KB pages that just store the data, and you point to that other page, so that you can have the consistent size of rows. So this is called overflow page typically, and this is where the problem with like storing too many things in a row comes up, because if you okay, basic questions. How many of you understand what is the main cost related to database? Like what determines performance when you read something from database? Like which metric, like CPU, RAM, disk? What are like few metrics that determine is it how fast it is going to be? RAM. What else? Huh? CPU cycles. Less so. Like disk I/O and RAM are the most likely indicator of performance, because if you read one page and you don't get the entire thing, like it tells you, okay, to read this row, you need to go and read 4 other pages to get the text varchar. Then now you have to read 5 pages to get one row. Like you have to, because it is pointing somewhere else. If it is all in line, then you are more efficient than this case. So again, the more indirect data you have, the slower it starts to get. But it is not as slow, but you need to remember these things while designing schemas, like what is going to happen. And there is a very good application of this in our problems also, where we say, oh, 65,000 is the 65,000 something is the limit of row size that you can have. You hit it because you have this problem where you have too many things in line. Yeah, I was going to end this, and yeah, this is the practical implication where like max row size limit hit is a problem that occurs because you have too many things in line. But at the same time, if you move it from inline to a pointer, now you have too many disk IOs, so it like gets slower and slower. I can show you our config, and we can do some, if I can. Okay. So this is the default configuration. This is the default configuration that we use on Frappe Cloud. All of this is configurable, but this is what we start with. Again, this is probably old. No, this is the final one, right? This is the current one? Okay, cool. There are a lot of things here. The first thing is this, which is what is the storage engine that we should use. Again, it is by default InnoDB. You rarely need to know anything else. What is relevant to storage here is this, like where are you storing your data? So all of the pages are just stored as like giant files, per table giant files inside some directory, typically varlib MySQL, which is the data directory. Then other things that are relevant to storage here are No, I'm trying to find something else. Oh, yeah, so this is the thing that like we create each file for each table. So each table has all of the pages in its separate file. And there is one more thing. Anyway, you can ask ChatGPT for explanation of all of these things, but I'll just cover storage related things for now. We'll come back to this again when we touch the other things. So any question related to storage so far? This covers broadly how databases store things on database on disk, which is this. Any questions on this so far? Yeah, shoot. Yeah, so page size is, so databases, so okay, the question is, I said page size is few KBs, so it might not include all the rows, right? So yes, page size is, so disk page are 4 KB. So when you say I want to read something from disk or write something to disk, you talk in terms of 4 KB. Even if you want to modify just one row, you read the entire thing, you modify that one thing and you write it back. Same thing in databases. If you want to modify one row, you don't just modify one row. You read the entire page, you change just that row, and you write the entire page back. We'll see it is not as inefficient usually because they figure out optimizations on top of it, but your unit of change has to be in pages. You do not just modify one row, you modify the page that contains that row. And now if you have too many rows, obviously you can't store all of them in one page. So you do have many, many pages. So this is 1, 2, 3, 4, 5, dot, dot, dot. These are all pages that represent different rows. And you can keep adding more and more pages. The storage manager takes care of how to create more pages on disk. Pages are just like a concept for us to visualize how it is getting handled, but deep down it is all bunch of zeros and ones in sequence. Like it's not like a construct that exists somewhere. It's like you just say, okay, I want to read 4 KB from here, 4 KB from there. So imagine like all the rows are written in a book. Like each page contains some rows on it. The next page contains some rows on it. So it's like a book and pages analogy. The pages just means some sort of container to hold things. Again, it's not a real container, just a construct that we used while discussing these things. Any other question? One more, okay. Okay, cool. So this is storage. Then the fun part comes, which is how the storage and RAM are managed together. So that is where the second part of this comes in, which lives in RAM, which is called buffer pool. Like I said, buffer pool is again just a whole bunch of pages, but it is usually smaller than the entire database. If you are doing things sanely, like if you're not wasting money, you have a buffer pool that is usually typically smaller than the database size. So like picture here that there are 5 or 6 pages on disk, but you only have a buffer pool which has capacity of 3 pages, or rather 2 pages, because first thing is just a directory of where to find what. So the job of databases buffer pool manager is to efficiently bring things into memory and then throw them out of memory when you don't feel it is required. So picture like typical ERP use case, because at least half of you are from that domain. So in ERP, if you are reading sales invoice or something, it will load sales invoice data in memory. But if you then go and do something else, like read some other doc type, and the buffer pool as capacity has run out, it will evict some of the things and load that thing into memory so that whatever you are reading recently is all in buffer pool. Now, what is the general term for buffer pool that you might have heard? Like, what is this doing? Like, it is speeding up some disk read cache. Exactly. So buffer pool is just a very fancy term. It is basically a cache for things that exist in database, because we don't want to reach disk continuously. So we build like this cache layer which reads from disk and gives you a faster access. Now it is not like the reason why it is called buffer pool, and it's like we don't use the general term, is one thing, it is specific to database, but other thing is databases generally tend to override a lot of what operating system does, because operating system also has a cache for things you read from disk, right? Do you know like file system cache? Like if you read something from disk, like if you read and load a 1 GB movie from disk, you will have a, like I can show you, why am I? If you see this, like the yellow thing you see is a disk cache, which means I have read enough things from disk that I might read it again. So the Linux is like, okay, you have 16 GB of RAM. I'll just keep it around for a while. But the difference, okay, yeah. The difference is databases do not just rely on the operating system. Now, why that might be the case? Why don't they just use the file system cache and they implement their own cache? Operating system might just flush the cache whenever. That is partly one reason. But what is a better rationale? Like when do you say, okay, I know better than you and I'll write better cache implementation than you? When can you usually say that? Yeah, so it knows, basically the benefit is it knows more about your data. It can learn more about data access pattern than just treating them as like blob of files. For files, you might not have, like operating system might have some idea, but for database server has much better idea about what you are doing with your query. So it can be smart about what to keep in memory. So that's why they override a lot of operating system functionality and try to be better. And in general, they are always better than the default database behavior, default operating system behavior. So, so one thing we understood here is buffer pool is basically a cache, but it is not just OS thing. Like they build their own thing. And this is not just MySQL, like Postgres, any kind of database you take, most of them have same implementation. Now, you have a few pages, like I'm just showing here 3 pages. In typical buffer pool, like I said, like there could be million, 2 million, 10 million pages. So you need to, 10 million slots for holding pages. So you need to keep some kind of a manager so that you manage the buffer pool well. And typically it is called page table, which just maps which page is assigned to what slot. Like if you have a million slots, then you need to make sure that you are utilizing them completely. And when you have to load something, where is the empty slot? So in general, it is a hash table. Hash table is just like a dictionary where you map page to a buffer pool frame. Like where is this buffer pool is just a whole bunch of slots. They call it frame, means slots. And you put a page into a slot and you keep track of it. Now, this is not just for sake of tracking what belongs to where. Like you, obviously you want to quickly access where a particular page is, but you also want to track, okay, which page got dirty, like who has, which page has modified data that I need to write it back. Or it might be locking things, like you might be locking a page, or concurrency related things. So all of the metadata lives in this kind of page table. And this comes in handy when you debug performance problems. Like there will be page table related metrics and you can see there is some spike in, or some contention on these things. So you can visualize what is happening there. It is, the contention could be because there are too many pages or too many operations going on. Anyway, so the fun part about cache is always the eviction algorithm. Do you guys know what are like typical eviction algorithms? LIFO is very bad eviction algorithm because you just remove what you just read. FIFO is a half decent algorithm. You remove the oldest thing, first in, first out, like whatever you read the oldest, you remove that. What else is a good? Last used, first out, which is LRU, least recently used. Yeah. There are several of them. There is LRU, which is last used, first out. There is LFU, which is least frequently used. You, whatever is just accessed like 0 or 1 time, you throw it out. There are so many. There is clock, there is LRU, there are variants of LRU. All of them have some trade-off. Like there is no magical oracle of cache eviction because you can't predict perfectly what is going to happen in future. Like they can't predict the future access pattern. So you decide what to evict based on some heuristic. So this is always some heuristic. Now, LRU is the common eviction algorithm in Redis also. In your in Python, you have LRU cache, which can memorize few things to avoid computation. LRU is very simple. Like whatever, like imagine like a linked list where you just keep track of what was read recently. As in, like okay, this is the linked list. Like ignore the other semantics, but linked list with the oldest thing that you read is uh, is at the end, and you just keep appending whatever you read at front. And whenever you read something again, you just move it from end to front, so that like whatever is read recently just stays at front, and eventually things get pushed to end if they don't read them enough, and you just throw things out at the end. So that is how a basic LRU works. Now, databases can't just use basic LRU. Why? Because like I said, like all cache algorithm, eviction algorithms have some problem. They are not optimal. What is the problem that would happen if you just use basic LRU? Accessing? Not sure. Okay. Well, yeah, LRU does not optimize for frequency. If you're reading something frequently enough, even and if you don't read it for a while, it goes to end. It will be thrown out. It does not because if you optimize for recency, you cannot optimize for frequency. That is one thing. There are other cases. So most heuristics algorithm have this worst case scenario. What is the worst case scenario for LRU cache? Yeah, exactly. So imagine like use case of ERP only, where you are all there are several people using the like reading transactions or going through list view, and one person comes and runs a report that scans everything. Now that person will throw out everyone else's cache, so everyone else's things are slow. The report is fast, and report if you run it again, it will run fast. But like who runs the report same? Who is dumb enough to run the same report multiple times? Like you, the 100% of the okay, bad example, but in general, you don't want to just allocate all of the RAM for one user who decided to read everything, right? Like you want to give them some RAM for sure, but you don't want one person, like one worst case scenario to throw out everything. So you need to be somewhat smarter about this. So that's why there is this variant called LRUK, which is least recently used, but you have like multiple generations. Like if you use something more than one time, like K means basically how many times you have used it, then it is moved to a separate LRU. That you just have like two LRU things. So anything that is read twice is more likely to survive, and anything that is read just once, like if you just read something for sake of report, it is in a separate list. So that separate list gets evicted faster, and the something that gets read multiple times gets evicted slower. It's just again like heuristics on top of heuristics, not necessarily perfect. Like if now the same problem is if you have users who run things twice, then they can still clear everything. Uh, but in practice, doesn't happen as often. It is not optimizing perfectly for frequency, but it is optimizing for at least one repeat use case. And by default, MySQL approximates LRU by this like two queues. So instead of having like one single FIFO queue, you chop the queue in two halves. You insert older things in the middle. Sorry, am I missing it? No. So if you read something first time, you put them in the middle so that they will get out fastly, okay, quickly. But if you read the same thing again, you will give them much better chance of surviving by putting them at top. So they will have longer time before they are thrown out. But so those who are reading report or backup is another operation that reads everything, but not necessarily. You don't backup twice. Makes zero sense. So like think of like things like version table. So version table will be put here because it is not, it is just accessed once for backing up, and it will go out and get cleared. And all of the things that are routinely read by users multiple times, like your transaction settings, they are living here because they are read multiple times and they go at the top of things. So you approximate the eviction algorithm like somehow. Like these are all heuristics again. Then there are papers after papers for optimizing better cache eviction, or this just works though. Like it's been there for 30, 40 years, still works. So that is the cache eviction algorithm, and all of these things you can kind of track, by the way. And I don't know how many of those things I can show right now because I'll have to worry about time. But if the time permits, I'll show some things. So let's first see our config again, the same config. And now we'll look at things that affect this buffer pool things. So if you see in on Frappe Cloud, we store buffer pool size by as a not a static thing, but as a formula. And the formula is rather dumb. It's not something smart, but this is the default config. We have the smartness that comes later, I think, right? Like the default config is basically take whatever memory you have, as it is in Ansible. This is a variable that tells you this machine has such MB of memory. You just take 60% of it, and you round it off, and you say this should be the buffer pool size. Now, there is no golden answer here. The way to determine buffer pool size for a particular machine is roughly 40 to 50 to 70% of your total size. So you have 4 gigabyte of machine, then you want to use at least around somewhere around 3 GB. But that doesn't make clear sense all the time. Like all of these are just thumb rules; they are not accurate. So on a for instance, on a 4 GB machine, if you just say 3 GB will be used for buffer pool, then only 1 GB is available for operating system and all the other things that are running. So you need to do some math. You can't just be this dumb about it. We were this dumb for a while, but then we got Tanmay and he fixed it, I think. So the smartness is basically figure out what is available RAM, not just the total RAM available on the machine. Then you have to do some math. Again, the details I will not go into. You have to do some math about what is statically allocated to other things and what can be utilized for buffer pool. But in general, if you have large enough machine like 8 GB, 16 GB, this rule works. You just use 60% of it for buffer pool. Yeah, this will change for unified versus dedicated also. So if you have 8 GB unified server, then you might not have all 8 GB for database. And this is partly the reason why people put database servers separately, so that database servers get the complete resources. And these these services or this software is also usually designed to be run like utilize as much as possible. Like whatever resources available, it will try to utilize as much as possible. So they are also not designed to coexist well. Uh, I think we weren't supposed to say that. But yeah, that dumb thing works for now, but at some point we'll have to figure out how to isolate it. I think we discussed the memory isolation with containers or C groups, where if you isolate it at kernel level, where you say that in a unified server, half of it is always allocated to database server and other half is always allocated to app server, then it works because it will not, the app server will not go beyond what is allocated to it. Like if both are running in the same machine. But if they are not, then they both can kind of kill each other by, yeah, by running out of memory. So managing all of that is pretty hard. That's why the two server solution is the simplest hack, where you make sure they are just physically isolated and can't mess up. But this is the most important configuration on any database server, by the way. Like if you don't configure this right, none of the other things matter because you are just not utilizing the RAM at all. So just make sure whatever, like on your cloud console or if you are self-hosting, just make sure that the buffer pool size is at least 50 to 70% of the available RAM. Now, other things here are not as interesting. Anyway. So the next question, next implication is how do you recommend DB server size? So this is how data is stored in RAM. Now, based on this, what do you think should be the ideal RAM size for a particular database? Like if you have 100 GB database, what should be the ideal RAM size? 100 GB is, it's not ideal, that is perfect, like you have perfect performance, but you are also you are also spending a lot of money which you might not be needing. So how do you decide what is the ideal RAM size? I get asked this quite a lot, and my answer is always it depends, because that is the general engineering answer to all questions. But there is some formula here or some heuristics here. No? No? And we want to think from DB internal's point of view. In general, no, because DRAMs are random access. In general, no. Practically, yes. Like very little difference. Like if you go from 16 GB to 256 GB, the RAM access will not be slowed down. But you will not notice it at all. Like this is we are talking at like very low level hardware. Doesn't concern us much. DB size is 100 GB. What is the RAM size you recommend to a user that you should use this? 60% is again just the number. 60% of your database size. Okay. So that 60% of buffer pool and this has no relation, by the way. Anything? How do you recommend? Again, there is no concrete answer here. That's yes, it would be dependent on what is the application that you're running on top of it. It would be depending on how you are using it, what is the access pattern, how much of data. So again, the first thing is, it is a cache, right? What is the ideal size of a cache? It should be small. It should be as small as possible. So you are not giving money to Bezos for no reason. Right? Like you want to give as little money to Jeff as possible. You can't just get 100 GB and pay them a lot. And RAM is getting pretty costly, by the way. Like it is 10x what it used to be a year ago. So don't just get 100 GB machine. No, pretty bad idea. So, okay. So the generally accepted conventional wisdom is the RAM size should fit your working set of data, quote unquote working set. This is the yeah. Yeah. So your disk, if you have to define what the working set of your data is. So working set of your data is imagine like 99% of the time, what is your user going to access? They are going to access recent transactions, right? Like they are going to access like last 1 year of transactions. Who in the right mind accesses like 10 years of data all the time, right? So roughly 1 year of data is your end user is going to access continuously. For reporting, you can assume some slowdown if they go and generate a report for 10 years. But like try to picture what working set is for your user 99% of the time. You can't say 100% of the time because then you've gotten everything. So 99% is roughly the number we target. And I will show you that how to measure that number also in practice. Do we have Frappe Cloud? Do we report BP miss ratio in cloud? Okay. Again, so this was generated long ago. This slides are old and we have this report now, so we don't have to size. It is a chart? Okay. So if you go and look at DB server, I'll have to see analytics. So we'll go through all of these if we have the time, but one of the interesting ones here is advanced analytics and going and looking at like buffer pool. Oh, so it's telling me to take a walk because health reasons. Anyway, so like this is the one thing that you should measure, which is what is the total RAM size and how much are you allocating it to buffer pool. So here we are allocating continuously 60%, which is good enough. This is the other report that you should look at is buffer pool miss percent, which is again the fancy term, but it is just cache misses. How many times you are missing the cache and going to disk. So this has to be less than 1%, which means the 99% of your access should be from RAM. Up to 1% from disk is roughly okay. And this is pretty much zero for us because our database, we have over provisioned, we are wasting money here for sure, but we don't care as much, so you're just leaving it here for now. This is our own private server, so we don't care so much. But for other servers, you will see, if I don't remember, do we know any good example where this will not be zero? Okay, let's not show customer data. This is our own data. So but it will show you some real number here, which will not be zero. If you are utilizing it correctly, it will not be zero. So you should monitor this. If it is too high, that means your buffer pool size is too low. And you need to add more RAM or configure the buffer pool right. If it is too low, like if it is zero, then you are wasting RAM. So we are definitely wasting RAM here. Yeah. Yeah. So there is the ideal RAM size for a current database is always known after you use it for a while, and it has to be, you have to go up and down, and you don't have to optimize too much because the machine RAMs are available usually in multiple of 16 GB, 32 GB. So you settle somewhere in between where it is like slightly more than what you need, because you are also growing over time. So you don't want to just perfectly optimize for it. You want some overhead, some headroom there. So this is how you uh, pick buffer pool size, RAM size. Is I can just keep the working set in your head. That is the term you will hear online also. You need to define the working set for your user. And the definition for that can change very wildly. Someone could be, like you might have, like two customers can have 100,000 transactions, but one would be reading 100,000 transactions in a day, and another would be reading 100,000 transactions in a year. That is very different memory requirement, because the other one can wait for a while, doesn't matter so much. So I showed the buffer pool size, the buffer pool miss ratio. The subchain churn is rather, anyway, we'll skip it. It is not available on cloud front end. I'll skip it for now. But it basically just says how is this algorithm performing. Like if you have a degenerative workload which is like backing up things twice, then it is probably messing up this algorithm or this heuristic. So in that case, looking at that number helps you identify that problem. But I don't think we run into this. Like I've seen it once in my life, so it will tell you that you have that problem. Then you have to go and find where the problem is. You'll not get the quick and easy solution most of the time. But imagine like if you're taking backup successively twice, then you can screw up the entire cache, and so you will have slowdown around that period of time. And you'd be like, why are we getting slowdowns here? It's because you have something that is reading the whole thing twice, and that is completely messing up the internal cache, the algorithm for the cache eviction. So again, there are some more questions related to that thing, like how backups affect buffer pool. They don't affect as much if they just read things once, because they'll be in the smaller list and just get evicted. So not a, how many of you understand swap? What is swap? Okay. What is swap on operating system? Just quick explanation. Yeah. Okay. So when the RAM is full and someone keeps demanding, oh, I need more RAM, you just go to disk and treat disk as a very, very slow version of RAM. Uh, why you should not rely on swap, or because it is slow. Okay. But particularly, why is swap bad for databases? It will add no, I mean that is okay. Latency, we assume latency is there. But if database server starts swapping, as in database server says, okay, buffer pool size is 4 GB, but you only have 2 GB of available RAM, so the 2 GB of the buffer pool will live on disk and will access it from there. What is the problem that is happening? Yeah, what is the point of the buffer pool, right? The buffer pool is like a swap implementation. This is swapping. Like swap is called swap because it like literally swaps data from disk to RAM. Yeah, so then it is a reverse swap when you are writing. So if you have another swap on top of it, you are doing 4 times as like twice as many operations. So like 4 total swaps for no reason. You have to reduce the buffer pool. So no. So you can have 4 GB buffer pool on 2 GB server. Oh, well, thank you. Yeah, then it is pointless, right? Because you are reading from disk to bring something into memory. Then again, like in the memory also, it is sitting somewhere else. From there, you are bringing it to buffer pool. So you are doing 2 hops, and every time you do 2 hop, you have to clear something also. You do 2 hop to throw something out. So you are wasting quite a lot of time. So on database server, swap is always bad. But like you can just take it as a thumb rule that if you have swap that is actively used, like you can have minimal swap where your operating system, other processes are going, like your monitoring agent or something that is not used. Like if that starts swapping, that is okay. But in general, having active swap usage, which you can measure, I don't know, which particular tool tells you how like IOTop or something is the tool that tells you how much your swap is being actively used. Like you can have 200 MB of swap usage, but if it is not frequently accessed, then it is not so bad. But in general, just try to avoid swap, like set swappiness to 1 so that kernel will not try to swap as much at all. It will just keep everything in memory, which is the perfect solution for databases. And you have to configure things right also. Don't configure more buffer pool than what is available. That is the stupidest thing we can do because just breaks down the logic of this. Like you have, so you can change, like I don't know if we have done that smart work or not, but you can change the swappiness by process, like which process should be using more. So why database just does not directly read from disk when the pool is full? That is the question, right? Because the general assumption is whatever you are reading from disk is likely to be read again, right? This is the cache, right? So if you are reading a new document and my buffer pool has older documents, it is more likely that the new document that you just read, you will read it again. So it is better to optimize for repeat access than to say that my pool is full, like I will now everything else will be slow, but the whatever is in pool will be fast because pool will contain old data, like whatever you put. And this feels dumb for like a few minutes of year, but database servers are typically up for years or months. So they need to be smart enough to continuously adapt to what is the new thing that are being read. And you usually read what you create recently, or like things like settings that are always accessed every time you open database, every time you open your application. So database need to be adapting to several days of uptime where they continuously optimize for the best performance at that time, not at when they were started. Does that answer? So we don't clear the entire buffer pool because we don't know how much to clear. So when you need, the way eviction works is, if you need to load one more page, it will evict one more page, just one page, and it will replace it with the thing you read. It is always trying to be as optimal as possible, not just clear everything and load new things. Because you might have just cleared what is going to be read next. Yeah, yeah. Yeah, so it is smarter. Okay, it is smarter. It will not write it back to disk if it is not changed at all. Like if you read something from disk and if you did not modify it, there is no point in writing it back. The swap cannot be that smart. That is why again, like this swap implementation exists because OS swap implementation is not smart. OS swap, if you read something from disk and if you modify it, it will have to write it back. If you don't modify it, probably doesn't know how. Okay, that is kind of misleading. Again, we are going too into OS details because OS is also smart enough to figure it out because the pages are marked as read only and then they change it. So, so we don't know for sure. Most used things will still be in RAM, but the things at the end of the list will likely be in swap and will be double swapping. So in general, just as a thumb rule, just take it that you do not want swap to exist with another swap because database is optimized for complete control of operating system, complete control of the hardware, and operating system is also assuming complete control of the hardware. So they are both competing with each other, doing the same thing. So also, databases bypass all of the disk IO. Like they do not go via operating system. They do not tell operating system cache manager to give it to them. Like there is this thing called O direct. Maybe like if you see here, I can show you. Yeah, this flush method called direct. So if you read the description of this, direct means just bypass operating system completely and write to disk directly. So they do a lot of bypassing. The database servers do a lot of bypassing. So that is why an operating system does not even know what it is doing. So if they are both competing and doing the same thing, they'll do it very poorly. Uh, okay. Enough questions for now. This covers the buffer pool entirely. If you have more questions, we'll do it later. So this marks the end of the first hour that was allotted, but I'll likely need more time. So I'll eat up some of the time from the tea break, like at least 15, 20 minutes. I hope it is okay. Cool, cool. And it is early morning, so you're not sleepy yet. So next part is indexing. Uh, So indexing is a there is a lot going on in indexing, but we'll just cover B plus trees because these are the most common type of indexing method. This is the most common type of indexing method. So how many of you know what B plus tree is? 1, 2, 3, 4, 5. Okay. How many of you think this is binary tree? It is not a binary tree. It looks like a binary tree. It is not binary tree. Those who know B plus tree is not binary tree, why do you think it is not just binary tree and it is something different? That is partly true. I mean, like that is a factual difference between the two. But what is the key difference between binary tree and B plus tree? It is not the most important difference. Again, not the most important thing. You can add the links to binary tree. Won't be such a hard problem. What is the most important difference between binary tree and B plus tree? Not the important difference still. So okay, no, no, so all of you understand binary tree at least, right? It is like you have a sorted thing which each node containing some data. Like imagine picture like here we are just storing numbers. So each node will contain some number that is binary tree. But the difference is in binary tree at each node you can just have one data point, and in B plus tree you can have n number of data points on each node. So this last node here it is showing 2 data slots, but you can have 4, you can have 10, you can have 100,000, whatever. So by definition, because you have more data here, like the B plus tree is going to be shorter than the binary tree, because if you had to represent all of these numbers separately, you have to go down, and it will be much larger. So the depth of B plus tree is usually smaller, and the width of B plus tree is usually larger. Now, why that is the fundamental difference, and why is that? Why does that difference exist? Why though? Why is so for sure lower depth is preferred. Like index should be the depth should be lower, and where you are storing data should be wider. But why it is important? Yeah, you'll be doing more traversal, but what is the cost of traversal here? Like each traversal is going to some page, then another page, then another page, and each of those is a disk IO, right? So like the B plus tree is mostly optimized for disk IO. Like it is as fewer disk IO as possible you want to do to reach the target thing. So even though B tree is like the binary tree is optimized for the log n traversal, it is not optimized for least amount of operations. So you want to reduce the number of IO operations you do. Again, the things that we learn in CS where the most optimum thing is log n does not hold true when you have to worry about disk IO. So that is the reason why we have this. So this is a typical index structure where your data lives in the leaf node, like the last level you have the real data. Here the data is just number, but your data could actually be like primary key and the rest of the data. That's how MySQL stores it. Like 6 could be the primary key, and somewhere hidden here would be the actual data. 6, the customer name, ID, items, whatever. You store all of them in sorted order because that's why it is called index. It is storing in sorted order, so you can find things quickly. The way it is represented is you have some root node which tells you where to go. Like if you're trying to find 6, like you go to left because everything less than 20 is here. Everything less than 10 is here, so 6 is here. So that is how you find it. Finding thing is more or less similar to how binary tree, you just do like a traversal of it. But like, it is somewhat complex because you have multiple nodes here. So let's say you are trying to find 7, which would likely live here. So you will not find 6, but you'll have to keep going in that direction to find 7 somewhere. And that's why you have these, not for a specific reason, but like if you want to do a range scan, like give me everything between 6 and 31, you can find 6 and you can keep going in that direction until you hit 31. So you are like your range queries are much faster. Like you are not doing find me 6, find me 7, find me 8, find me 9. You just keep traversing until you hit the range you want to care about. So that is the reason for these links at the last level. because you can quickly scan the whole thing. And like I said during the storage, like I'll have to explain this later because these are all linked concepts. So in storage, your InnoDB, like MySQL stores or everything like this only, where your data actually is in the last node. This is not how every database works. Like Postgres does it differently. Postgres stores everything in random heap file and then arranges by index. But MySQL by default organizes by index. Okay. I just said this. Okay. So now this is the primary index, but you can add more and more index, right? Like primary index is your name or ID field if you are using some other framework. But you might also want to index something else like anything. Okay. Like the customer of you might want to index sales order by a customer name. So for that you have to create something called secondary index. So every index you add yourself is always secondary because primary is the primary key. So what do you think secondary indexes do? Like they are also a structure like this only, where you can quickly find a customer name. So in the primary key, you have the actual data, like you search by name and you find the data. The secondary key basically just tell you where to find the primary key. Like they'll just link you to the primary key. Like it will, if you say, give me all orders by customer XYZ, the data here, like this is the key and value. So like 6 would contain, okay, customer ID 6 has these many sales order, and you then just find each one of them separately by querying the original table. So anything you read from secondary index requires some indirect access. It cannot just directly give you the entire data because you definitely don't want to duplicate the data for every index. So it is just a pointer to your primary key. Now, this works, like secondary indexes work most of the time, but then there are these cases where you might want to find something by 2 different columns, and you can't do it by adding indexing 2 separate columns separately. Because like just imagine this scenario only, right? If you have 2 separate columns, you want to find a combination of these 2, you can't just traverse them together separately. So what you end up doing, okay, just give me a second, could be something important. So what you end up doing is you basically concatenate 2 things. Like then the simplest example is your names. If you want to find people by first name and last name together, like just merge them together and create like a new field called full name. And then you can index the full name and that will be faster. But doing that manually is quite stupid, right? Like every time you want multiple column search, you don't want to like create a new merge column yourself. So DBs just do it by default internally. If you say index these 2 columns together, they will create like this index where the first name and last name are stored together. So when you say search Alice in chains or something, Alice chains, it will find the first thing. We'll do some demo of how index the B plus tree actually works because that is more useful than me talking about it. Okay. If this loads, which is anytime now. This is just dumb static page. Why is it taking so long? Okay. So so there are basically 3 operations in binary trees, right? B plus trees, which is insert something into it, delete something into it, and find something. Update is also there, but that is just find and update. That's nothing complex because update can. So we'll not consider all the corner cases, but basically it is insert. So we'll start with max degree 3, which means each node can max have 3 different things like we saw before. So in binary tree, the degree would be 1. Like each node can only have 1 data point. It cannot have multiple data points. So we'll just start inserting random thing here. So if I insert 2, it will go next to that. Now if I insert 3, that will go there. And it will split itself because it cannot store more 3 things at the same node because the degree is 3. So like all of these, that's part of just the standard B plus tree algorithm, how to split nodes, when to merge nodes back. So if I delete 3 right now, it will have to again merge them back because You don't want to have, okay, it won't merge because that is not a problem. But if I delete 2 again, now it will merge and again go back to being the single node. So let's do some more random examples because usually don't insert thing in sequence. So like 6. Now if I insert 3, where will you think it will go? Right side? On the between them, and what will happen? They will be split. They were split, and what happened is not like the another level was created, because usually don't create another level. You like the root node had more space, so it went up. And that you will notice, like B plus trees are always balanced, like they don't have uneven depth. Let's add, what should I add? 5? No, something creative that gives you some different. 10? Okay. 10,000. Okay, 10,000, 1,000. Okay, so this is what is happening. So the point is not to understand the whole algorithm, but you can. But when you add data, the internal index structure is also continuously being modified. And for instance, if you rename index, like if you rename primary key, this kind of rearrangement will happen. If you insert, this kind of rearrangement will happen. If you delete, this kind of rearrangement can potentially happen. Like it's not like every operation will do it, because if there is enough slot available, it will not do it. But it is likely that that kind of thing will happen, this rebalancing. And this is called index maintenance. Like you have to maintain it so that it maintains the properties of same depth, say max degree. So the more indexes you add, the more maintenance you have to do everywhere. And that's why adding indexes also becomes costly. Like because all of this operation costs time. You have to lock things so that others cannot mess it up in between. So the point of showing it was just like what is the operations involved in maintaining this. So, okay. So I just have 2 examples here. Like what are the practical implications of how indexes work? One thing is primary naming matters. And there is this PR by me 2-3 years ago, where like what is the, those who know Frappe, I think 80% of you, how does hash naming work? Like what is hash naming? No, that is the new thing. But what is in general? What is the promise of hash naming? Just random hash, right? Why do you not want random hash in things like this?
Because most of our data is sequential in nature.
E-
So we want like the indexes to be also organized in a way that the
Yeah. So let's say you insert like 10 child a sales invoice with 10 items. They are usually they should be inserted together, right? Like because they are going to be accessed together, updated together, deleted together. They are, but if you put like random hash as your primary key, then they will be spread all along the database. Like some will go here, some will go there, some will go there. And this is very clearly visible in the old implementation, where it was just the hash was truly random. Now it is not truly random anymore. But if you see this, I mean, I don't have the actual benchmarks here anymore because it's 2 years old. I can't find it, but basically a single document that had 1,000 child tables, and while reading it, I measured how many pages we were accessing. So when there were 1,000 child tables in a large database which had like several thousand pages, if you insert 1,000, all 1,000 of them were in different pages. So you had to index go through this index like 1,000 different times and find one row from each different page. So you had like 1,000 times 4 KB IO, that much IO. But if you all stored them roughly linearly, 1,000 of them fit in, what is the, okay, I don't remember what those numbers mean anymore, but like roughly 100 times reduction you can observe, because you can't get perfect 1,000 time reduction, but they'll read fewer and fewer pages because all of the rows will sit next to each other. This benefit is also there in like when you have naming series, because if naming series is sequential, then all the data will live next to it. This is also there in integer primary key because they are also sequential. This is also there in UUID because Frappe UUID is UUID 7, which is sequential. Yeah, because it has the timestamp in front, and this also, like this is very clever hack, where the instead of just being at random, the first few part are some timestamp. So it is timestamp encoded as hexadecimal. So it is somewhat sequential when you insert it at the same time. It is makeshift because it's not real. So these are the things you need to worry about when you have like high throughput ingestion. So if you don't have UID or primary key in high throughput ingestion, like they'll be spread all across the database, and it will be slower than if they were in the single layer. I think RTCamp is not here, but like they showed one example where they benefited quite a lot from switching to UID in the high throughput example. Mm. UID is only available in v16 though, and not yet available on Frappe Cloud, but I hope it will be available soon. I hope the Frappe Cloud team is listening. It requires a newer version of database. Uh, cool. So anything about indexes? Any questions about indexes? This is the last topic, by the way. We'll break for tea for 40 minutes.
So let's say if I don't care about the storage space,
Hmm.
so will indexing all the columns help?
So again, indexing has cost. The one of the cost is this whole maintenance. So when you insert or update something that has index, all of this internal data structure has to be updated, and this has to be updated in consistent manner when the concurrency exists, because
Let's say even I don't care about the write speed, only just reading the data.
probably helps. If you just care about reading the data after it is ingested once, it probably helps. You trade off the storage for this. Again, there is no rights. There's no perfect answer to all of these things. It most likely helps if you are just reading the data. But if you anytime you have to do updates, then it is costly. Your insert speed will also slow down, because while inserting you'll have to maintain all of these things, and if you and your reads also determine how this will slow down, because your reads can also be locking in some sense, that I want to update these things, but in your example you are saying you are not updating anything. Like it depends, and some of the implications I cover in the concurrency section, like why too many indexes are bad from concurrency point of view.
Are they also stored in RAM or are they just in?
Indexes are also stored in pages, because it's just like pages are just bunch of blocks where you can store anything. So indexes are also stored in pages. There are different pages, like you have index pages, data pages. They all have different internal structure, but they are just all 4 KB chunks or 16 KB chunks in case of MySQL.
And then they go to the buffer if required.
Yeah. So buffer pool also contains indexes. So when you request something via index, first you go to buffer pool to find index. You read the index, find the thing, go to buffer pool again to find where the actual data is. So buffer pool is accessed several times during the course of this. Like the this is not just data. It can contain metadata. It can contain indexes. It can contain images, text, whatever.
So, for example, a page can have more than one row.
Yeah.
So, will buffer pool have a full page or the specific row?
Buffer pool will deal with full pages only, not individual rows, because the unit of operation it knows is how to read a page, how to write a page. Conceptually, optimization internally they might be doing smart things, but conceptually reading a row and writing a row, reading a page and writing a page. The question is, can we have dynamic buffer pool? We can, but this is like 30-year-old technology. They don't have it. The buffer pool is technically dynamic. Like at runtime, you can tell MySQL that increase the size of the buffer pool, and that's what we do at Frappe Cloud also. Like when you update it from UI, it updates it dynamically. But by the way, those who want to leave can leave for tea. I will be back at 12 o'clock, and we'll resume for one more hour. Complete the answer. You can dynamically resize the buffer pool, and that will help you if you know, okay, at night I need more space for something else, and at day like if you have that oracle mind where you know perfectly when I need more and when I need less, you can do it. But most of the time we don't. And again, these are fairly old technology. They don't have internals of it. If you are interested in these things, read about this thing called self-driving databases, where this there are these modern new age databases that are smart enough to figure out when they need to scale which parameter. So the human does not do it themselves, but some other heuristic decides when to increase, when to decrease. We covered storage, how data is stored. We covered buffer pool, how data is managed or cached. We covered indexing, how indexes work internally. We haven't covered anything practical so far. We'll likely not cover in this talk anyway. But the next three things are how queries that you send are planned and executed, and concurrency, which is what to do when multiple queries are running concurrently, and lastly, a very small topic on how logging works and how databases recover from crashes. So we'll begin. The Unless someone has questions from beforehand, because we still have some time, so if you have questions, we can take them right now. Query planner is basically when you send a query. We all understand SQL, right? Like SQL is declarative. You don't say how to fetch the data or what to do. You don't do any instruction about physical operation. You just tell, give me this data, give me this aggregate or some of these things, but I don't care how you do it. It's in some sense like close to AI, you prompt it and you get the answer, but far more deterministic. But at the same time, when you give it a declarative definition of what you want, it is not necessarily it is not necessarily the fastest way to get it. So this is where the abstraction breaks down, where there will be some declarative definition of what you want, and there will be some physical version of that is going to be the fastest. So the job of query planner is to make sure that you get the fastest execution possible and the correct execution possible. You don't want just random things also. So we'll look at some examples here. So when you say join table A with join table B, I'm writing like sudo Python here, but what usually happens, just use Frappe's example, where you are joining child table with parent table. So child table's parent is joined with the name of the parent thing, and you get all the documents. So you might assume this is how join works, right? Where the join is basically for every row in outer table, just go through all the rows. For every row in inner table, if the inner row and the outer row matches, then you have one joined row available now. If you're joining all child table with all parent table. Does this make sense, more or less? If you cover, I should have written the SQL query on top, but anyway. The SQL query would have been join the parent table with the child table. And this is the one naive assumption in our head. This is just declarative assumption that this is what it's doing. What is the problem with this? It is called naive. What is the problem with this? Sorry? You have to be a little louder. I can hear you. It's a small room, but you have to still be a little louder. What is the problem with this naive join? It is n square, or not n, but m by n. We don't know the sizes, but roughly it is. So if you have a table of size m and another table of size n, joining them becomes m times n, which is way too large, because you are trying to see if every row of child table matches with every row of parent table, which is pretty stupid, because most of the time it is 4, 5, 10 rows match with one parent. That is our assumption, and that is true most of the time. So with that assumption, can we do better than just this naive join? What do you think DB most likely does? Instead of just doing this dumb thing. Well, sorry? Just louder? It's okay. It matches the ID using how? Name is the ID here. Yeah, so if you don't know, yeah, this is Frappe example, but name is basically ID, which is primary key. It matches primary key how? Indexes. So what usually ends up happening is you use one table and you fetch the items from other table using an index instead of just looping over all of them. So this is just a function, made up function, but basically use the index to find that predicate where the parent is equals to name, and you find all the rows, and now you can yield them without checking the conditions, because you know for sure that index is giving you the exact data you want. You just want all the parents where the name is sales order 1. So you are doing a lot of index accesses, but it is still way more optimal because you are not doing m times n. It is just m times 2, 3, whatever is the typical average number. So this is how index joins work. There are other joins, but I'm not covering too many of them. There is slides and there is this lecture also. You can look into how joins work, how the other types of joins work. Because the complex queries you write, it is not as simple as joining two tables. You might be joining 2, 3 tables. They might have some weird filters or subqueries, etc. So I'll not go through all of them, but I'll show you how beyond sort, like if you don't have index, what are the other things that happen? And you will see these things happening if when you do explain this query, you will see sorting or sorting table or sorting and storing table, sorting temporary table or something like this, like some kind of sort keyword. That means you are not using index, you are sorting the entire table first and then trying to merge them. So yesterday someone did the smart solution to anagram where like you just sort everything and then just compare sorted things. The same thing is happening here where when you want to join 1, 2, 3 with the incorrectly ordered child table of other, like the child table has links to the original thing. It's again poorly named. It's not ID, it's the ID of this original thing. It's like foreign key there. So if you want to join them faster, what you can do is you can sort them. Now it is all 1, 1, 2, 2, 3, and just iterate them with like 2 pointers. So like you can do get one from here and keep getting foreign keys from there which have one, and you have joined it effectively. So you sort both of them once and join in like linear time instead of m times n. So this is sort join. Uh, this is how it works. You don't need to implement this, but you need to know when you see sort join in your explain output, this is what is happening, and this is slower than index because you are sorting everything. There are more join types, which one of which is hash join. I haven't seen this in Blake. Postgres has this, but MariaDB does not so much. But basically, you hash both ends, like just like here you are sorting. On the other side, you hash both ends, and wherever they land, that is the join. So you hash primary key here, foreign key there, and they'll both land in the same slot in the dictionary, basically. So that's that's how it works. And MariaDB has this thing called adaptive hash index, where it just magically at runtime generates the hash table and tries to index it. Uh, I don't know if you disable it or not, but like this is usually cause of a lot of problems when it incorrectly identifies that it can use hash indexes. Again, something to know when you see it in explain output or some process description that, oh, it is building hash index or it is trying to use this adaptive hash things. This is what is happening. So I can't go into too much detail, but you can look it up when you need to. So this is about how joins work. That is one of the complex things. Now we move to the part where you need to understand how these things are executed. SQL is pretty terrible when it comes to the order of things that write. Like you select from where. That is not how it is executed. Like conceptually, this is how it is executed, and conceptually, this is how you should be allowed to write queries. Like there are new databases that allow you to write in this order, where like you choose from which table you want and join it with which table, filter what, group by. Like this is the order that is in our head. This is not how we write it because 50 years ago someone decided to not follow this format. But that's how the standards work. But in Query Builder, you can kind of do it in any order, and most Query Builder queries follow this order, like where you do from, join, then you filter. But is this the execution order also? And most of the time, you don't know what is the execution order because you are just declaratively telling this is what I want. And the execution order can be flipped, can be rearranged based on what is the fastest thing to do from databases point of view. Now we'll see what Query Planner does to make that happen. So first, you need to understand what the problem is. Like why the actual execution order is just not this. Because if you always follow this, then it is much simpler. Like there is no need for a query planner or executor. So like we'll take a few examples. This example is select everything from item table. What do you think should be the order of execution here? Like select everything from any table. This is the conceptual order. What is the order that is followed here? Yeah, so here you're just doing one from that table. There is nothing to do. You're just selecting everything. So it's pretty easy. It follows this model. Like obviously, you don't have to use where if there is no filter, but it is following the same order where you're selecting everything. Now, if that query changed and someone said select from item, but give me like 20 recently created item, Now, this, if you follow the conceptual execution model where you select everything from item table, then you move down up until you order it by some timestamp, and then you limit the 20 recent 20 ones. This is the conceptual order, and it will give you correct answer, but is it fast? It is obviously not fast, like, because item table can be growing exponentially, not exponentially, but it can be growing continuously, and you don't know what is the runtime characteristic of that anymore. So what can be done better?
So you order and limit first, and then you select the views.
Yeah, so you order first, order and limit first, but if you have to select everything and order it, isn't it the same thing? Like, what do you need to make it happen? That where you can order and limit first without checking everything.
You limit at the time of selecting.
You limit at the, no, that is no. So the problem is not that. So you need there's one missing piece here. Like, if you don't have it indexed, you cannot do the ordering magically, because indexes are pre-ordered. So if the creation field here is indexed, then there exists an index where you can just look at the index and say these are the first 20 items. But if it is not indexed, then you have to do the old conceptual thing where you read everything, first sort it, then find the first 20. So here the execution order depends on what is the schema that you have specified. If the creation is indexed, it will likely be, it is smarter to use the index and get the first 20 and not read everything. So this is the job of query planner, where it will figure out what to do which is faster. Uh, this is, everyone understood this example, right? It's pretty simple. It is called top N. Like, if you are looking into any query optimization literature, this will be called top N, like top 20, give me top 20 items, and it is usually optimized by adding index on the sort order. I'll cover some practical optimization much later, not right now. Now, let's make the queries more and more complicated. So here, this is example from stock module where you have stock ledgers, and stock ledger are this entries of, like, in which warehouse, in which using which item, at what time, what happened. So like you guys understand what warehouses and items are? Like, at every you track where your items are moving, like how much new item you got, how many items you sold. You track it per warehouse, and this is how it is represented in the code. Now, let's say you're trying to select a particular item, particular warehouse after a certain date. Like, I want to see the first entry of this year. This is slide is from 2024, but I want to see the first entry of this year for this item in this warehouse, like opening balance. Like, this is the opening balance query, right? How do I optimize this? Or, like, as a database, how do I optimize this? So your suggestion is, if I look at posting date time, which will be sorted by this year, sorry, the date time, and I go and look at the first thing, it will be the fastest, right? Will it be? Is it guaranteed to be fastest?
You would need to first filter, right? So you would need an index on item code in warehouse.
Yeah, but then you don't. So, okay, there are two potential indexes, right? Like item code and warehouse to get all the entries for this item and this warehouse. The another is year. So, as a database, how do you pick which one is better?
First you filter all the
Cardinality.
You filter by cardinality. Cardinality is uniqueness, which means
So the lesser cardinality means much quicker results.
we haven't reached the cardinality yet. You're going ahead in syllabus. But that is partly the correct answer. It is not 100% correct answer. Cardinality is one of the reasons. So, like, first, let me give you an example where this breaks down, where you can't pick one or the other 100% of the time. So let's say you are using posting date time, which is like this date time index, and you say, give me the first entry in this year's entries, where this is the item in warehouse. Now, if this item is very infrequently used, like something that is very rarely used, so you might start from this year, and the first transaction might be done like 2 months later. So you scan 2 months of data to find this item, and it is not there. So, like, that is the worst case scenario for using posting date time index, because if the item is not frequently used, then you are wasting a lot of time trying to just find the item in that index. Similarly, what is the worst case when you use item and warehouse and not posting date?
if you have a lot of them.
Yeah, if it is used too frequently, For if an item warehouse is used too frequently, then you will have to find like there might be years and years of history. You have to go and find the history that starts at 2024. Like you'll have to separately sort it out. So both cases are not 100% ideal. What is the ideal solution?
I mean, not a triple index.
It is a triple index. So a triple index would have all of these concatenated. So it will know exactly where to go directly. Like you can have a concatenated triple index that will give you answer to this query in log n time, which is like the fastest you can do.
But then, I mean, that's the ideal situation, right?
Yeah. That's what we do in ERPNX, by the way. It's not made up. This is the,
Oh, all three are indexed?
yeah, together, not separately.
Yeah.
That's what we do now. Back when I made this, I don't think we did it back then. Rohit is not here. Okay. Oh, yeah, here. Yeah. We didn't do it in back then, right? This is recent. Right? Okay. Cool. Yeah. Now we have a fourth index. Yeah. We have the fourth is creation. You break the ties. Anyway, this is very specific to ERP next. But the point is like when you have a situation like this, you might have to do triple index or quadruple index, all of them. But database does not decide for you what index you should have. Like if you just have these two, then it has to somehow decide which one is better. So the way it will decide is by cardinality. But like it will see like this item warehouse combination, how frequently is it used? Is it used very rarely? If it is used very rarely, then I will have a better chance finding it in item warehouse index because I'll just get like 10 rows and I can just check which one is the latest one. Or if it is used too frequently, then I'll have better shot at finding it in posting date type.
So it would just check the cardinality for item code and warehouse composite index.
Both of them, yeah. It will check cardinality for both of them and see where is the cardinality likely going to. So first of all, everyone understand cardinality? I don't think you do. Cardinality, because I haven't explained. Like it came up too early. So we'll reach there. Okay, so we'll reach there one step at a time. So I'll explain first how to model this execution, like these queries. And the model is iterators. The iterator, this was an iterator, right? Like for you do 2 loops, and when you find a row that matches, you yield it to the next thing, and then it will process it. The yield is this iterator protocol. The same thing exists in databases where they'll read different tables and they will keep yielding what matches, and eventually you have the result that you care about. Now, if we have this query, like this is a different query, but it is a rather simple query. We are selecting item, and we are matching it to item group, and we want to select all items that have item group of product, and that is enabled because you don't care about disabled item anymore. So there are 2 filters here. One is it is enabled, which is stored in item, and the other filter is it belongs to product category, which is stored somewhere else. So there are because of these 2 filters, like this here also we'll see some funky things. So just picture how this can be executed. First we'll do the conceptual model, which is very simple model where you just do from first. We will scan all the tables in item. This is where we are scanning everything in item. We are sending it to whoever is going to process it. There we are scanning everything in item group, and we are sending to some join function. Now the join function will do the m times n join. Again, this is conceptual model, it's not optimal. It will do m time n join and find all the rows that match, and then it will yield further. It will try to filter, okay, where the product name is product. So now you have even fewer rows. You go up, you remove all the disabled items. Now you have even fewer rows, and ultimately only care about the name of the thing. So you just get the name and you return it to the user. So these are all the technical terms. Project means take some row and just give like a subset of it. A filter is filter out the rows. Like these are all operations, and they have symbols. And like if you go and read DB books, you find these terms. Scan just means read from the table. So far understandable, right? This is just the conceptual model in your head. This is not the optimal thing to do. Why is it not optimal?
Because you're scanning huge tables.
Yeah, you are scanning entire tables, entire rows, and ultimately you are just returning name. You are not doing anything with whatever. Like it could be like 200 columns. You are reading all of it. So the first thing, basically, this is sequential scan where you read each and everything and you see if it matches the condition, and you return the condition. That is what this conceptual model is like. It's just sequentially seeing each and every row and trying to find what is the row that matches and trying to join it. The better thing to do is you can use index instead of sequentially scanning, because name and ID probably index. If it is not indexed, you maybe index it, and then if you use index, then obviously you avoid the m by n join. You find the fewest possible things, and you can get the answer. The same thing that I explained before. Uh, so the the problem of query optimization then becomes like find the correct execution with the lowest cost, like the lowest possible IO, lowest possible memory accesses. And for that, we start this process of query optimization. The planning and optimization are all the same thing. So the optimization process, this query optimization is not you manually optimizing. This is DB optimizing the plan for how it wants to fetch data instead of doing the dumb thing. So this is roughly how most databases do it. So when you send a query, it goes to parser and it just passes it to some internal structure so that it can process it. Then like you can ignore all of these things, but mostly it goes to like a rewriter of sort where you can hydrate the query with more information, and you build like some logical plan which makes sense. This is a plan that is based on rules. Like you can say, you can transform some things. Like imagine Samgap rule. Like you can, instead of doing X, you can do Y. So like DB knows there are these transformations that are possible, and some transforms are better than others. So it can just automatically rewrite your query and just while keeping the correctness there. Then this goes to the actual optimizer, and optimizer has this cost models. So this is where the entire magic of query optimizer comes from, where they know roughly what your data looks like. Like they know roughly what is the cardinality, where you have, what kind of distribution you have, and knowing that, they can decide which plan to execute. Like they might generate several plan and pick the best possible plan. And all of this happens all on the fly all the time. Like every query you send, it is doing all of this. And it is so fast you don't even notice the time it takes to do the planning and all of this. And finally, you get the physical plan, which is using the logical conceptual plan, use the cost data, and build the physical plan, which is actually how to go to disk and find things, and like which we don't want to do. We want to be declarative. So the DB internally prepares the physical plan from where to get what data. So now we'll use the same old query, and we'll try to apply the same thing here. Like this is the query that we discussed: joining item with item group, finding filtering by enabled items, and filtering by products. So instead of doing the dumb thing of selecting everything and then filtering, then removing the columns, only keeping the columns you want, we can just select what you want. So here it is not that we just want name, we want more things here, because even though you just want to return name, but you want to compare group and name, like this product and ID, all of these things. So you have to basically figure out which columns you will need and push it down to the level of table. So from this table, I just need these 3 columns. So don't select the entire row, just select these 3-4 columns. Same thing there. So you automatically saved a lot of memory usage by just selecting the few columns that you care about and not all of it. This is called projection pushdown, where you just push down the whatever you need to select to very low level, and that's why it is somewhat more optimal. The other thing I was going to ask, but I'm going to tell anyway. So the other thing you can push down is by filters. So instead of filtering after all the data is joined together with giant m by n join, you can just say that this filter is entirely dependent on the group, and the other filter is entirely dependent on this. Like this is not a joint filter. So you can just say that that filter should move down to the selection layer, where you apply that filter first and then only you send it. So now you already have fewer rows to join. So and all the rows are already likely to be valid, not completely invalid. So you only select products, you only select enabled items, and then you join and then you return it. So these two are simple optimizations, but there are hundreds of such optimizations that DBs apply before they even think about how to execute it. There is one more which is somewhat simple to understand. So if you write a query like this where you have a subquery, but you can optimize it by rewriting it. Like instead of doing the subquery, you can just do a join, and you might yourself might not have to write a join, but like internally it will rewrite it and convert it into a join. And all of these are explorable by writing explain in front of your query and seeing what it is actually doing. So you will see if it says correlated subquery, then your subquery is executed every time. But if it is not showing that, then it is probably done some magical rewrite and you don't have to worry about writing it in perfect way. Again, this is same query that we saw before. This is a worse version of it with subquery, where you see if there exists a group with this item where it is product. Dumber example. But there is another simpler example where if you see this subquery, where you are trying to find, because we don't know the group ID here, what we are doing is we'll just write a subquery to find group ID where the group is product. Instead of joining, you are saying just give me the ID, and if the group and ID are same, then find it. So here also, this is not dependent on anything that happens outside. So you can just evaluate this first, and then worry about what to do with the rest of the query. And that's what MySQL does, by the way. So like it will just replace it with, like run the inner query and replace it with the actual value. So it will not execute in a loop the same query multiple times. So again, now we have seen 3 or 4 examples where the logical optimization happens. But the cost-based optimization happens on 2 things. One is cardinality and another is distribution. So far, we can't optimize without looking at data. Like here, we have to look at data. Like, is it item warehouse going to be better, or is date time going to be better? And like we discussed, we can look at cardinality. And cardinality is just how unique the data is, as in, or the opposite of it. Like for a particular item warehouse, how many entries exist in database? The fewer the entries, the better it is to use that index, because you don't want to read too many things and then filter it out. The distribution is something complex. It is not always enabled by default, but distribution just means for things like these, like posting date time, you might have data that is quite oddly distributed. So for instance, you might have 1 year where there isn't enough data. So even though the cardinality of posting date time is like, oh, there is a lot of unique data, but for a particular year, you don't have enough data. And so it can look at distribution of that also by like having like histogram of things. And if it vaguely knows that in this year there isn't enough data, so I should probably look at that so that the like I'm reading fewer and fewer data points. So these are 2 mechanisms. There are more, but MySQL being somewhat older database just does these 2 things as far as I know. You can inspect these things also. Let me see if I can show you something. So if you see this, this is a user table. Like all the columns are pretty much self-explanatory. So username is likely going to be unique because you need it to be unique. And if I have 100 users here, the 100 cardinality means they are all unique, roughly unique. And the cardinalities are estimates here, so they are not like actual number, but they are roughly correct. So all of these things, 100 username, 100 mobile number, 100 API key, that means they are all roughly unique. But like this last active index with 33, that means they have some duplicate data. So you will have like 1/3 the shot at finding the right thing with just 1 row. Or if you filter it by, you'll on average find 3 rows because 100 rows, 33 cardinality, roughly there. Some things are not there. You can't rely on this to be like, this is not going to be 100% accurate. These are all statistics that they maintain somehow. So this is the distribution. So for instance, like I'm also understanding this on the fly. Okay, so they are indexing name column here, and they do a rough histogram, which is like this probably starts with name starting with A, the end is probably name starting with Z. And you just see where the names are likely distributed. So for instance, if you do it in India, like Aditya is the most common name, so you'll probably find somewhere here a Spike because it's like the most common guy's name. Similarly, they are showing here John, Joan, whatever, like there are spikes here. So if you use this data, you can kind of figure out where the, like if you do like this range, you can tell that this does not have too much data. So if I have to find something here, I should probably use this index and go there because it will be very less data to read to verify if something exists or not. But if it is somewhere here, then it is a lot of data you are going to read because a lot of Joan and John, whatever. So this is how it works internally. It's not enabled everywhere. You can enable this on your DB server by enabling histograms. We do it on some servers, not everywhere. But this is, helps where you don't want triple, quadruple indexes, but still somewhat smarter execution. That covers query planner execution more or less. Do people have any questions?
So it decides when to throw out indexes as well, right?
No, no. When to throw out? When throw out means delete?
No, so when to use the index,
Yeah.
yeah, like the priority of the index, which one of the indexes to use.
So both cardinality and distribution are used to figure out which index is going to be better for this query. Because for same query, again, for this same query with different value, like if x and y change, the another index might be better.
So yeah, like throughout I don't mean delete, I mean like which index to
To
pick.
ignore, yeah. Which one to pick, which one to ignore. If you have two of them, sometimes the first is better, sometimes the second is better. It has to on the fly figure out which one is better because the user hasn't given any hint which one is better. And that is why like you giving hint is likely bad also. Like sometimes what we end up doing is we give hint that we profiled a query with some item warehouse and we found that this one is better. So we just force the hint into the query. Like there is syntax that lets you force which index to use. But then if the distribution changes or the another user has different distribution, then you are forcing them inefficient version while DB should have been smart enough to figure out which one is better. So in most cases, some configuration error is there if it cannot figure out the smart one, or you should change the schema, but very rarely you should force indexes without knowing for sure that forcing is the best option. So that was added because in some cases it was not identifying this correctly and we did not have histograms enabled. After enabling histograms, some of the queries got better because histograms tells you precisely what the distribution is. That is still not the solution. Ultimately, the final solution was just creating a triple index of all three of these together and then fourth creation. But basically, doing a better index was better. Like a better index was a better solution than forcing one of those because both of them were inefficient. Yeah.
But indexing also makes the time longer for write and update operation.
Yeah, yeah. So while inserting, if you have this triple index, it has to be updated like we showed before the B tree update, all the things. So it does increase the time, but it is like marginal increase in insert time with let's say you have 5 to 10 decent indexes. It's not such a huge problem. If you have hundreds of indexes, then yeah. There are other side effects of adding indexes. We'll see later, but in general, it does increase the time it takes to insert things.
Because in stock ledger entries, I can consider adding index and reading it from there. But do you do the same for GL entries as well? Because that entries get created more frequently.
We both have. I wouldn't say they have more frequent. The frequency depends on what your company does. Like you might have more stock operations than GL operations. So because GLs are aggregated stock, like for a lot of stock entry, you can have single GL aggregated, single or like rather 2 or 3 GL entries for a lot of stock entries. So it is not for sure that one of those will be higher. We do similar kind of indexing for GL entry also. Not this exact thing, but whatever is required. Any other questions? We'll come back to what problem indexes create later.
So suppose we have a composite index on the three columns, okay? So that works fine. But then if you have like single indexes on the three columns, so how like is it like resolved in this case? Like suppose we don't have composite index on the both
So
warehouse and the
yes, so the question is we have triple index and versus we have 3 individual index. How is it resolved? So 3 individual indexes usually cannot give you the same benefit as a like composite index because 3 individual indexes will all three of them are optimized to help you find X. They are optimized to help you find Y. They are optimized to help you find the something like greater than the range, but they are not working together because all the entries of X, like item X, will not have warehouse Y. So you have to once you use that index, you have to filter it again. You can't use two index together unless it's composite index. In rare cases you can, but that is like in cases where you have OR queries, you can like I'll give one example where it is possible. Where did it go? Yeah, so there is this only one edge case where like two individual indexes can help, and that is this case of or. Like if you have, like you want to filter by a equals x or b equals y, these are two different operations. Like give me everything that matches this index, give me everything that matches that index, and then you merge it together. It is index merge. So this is the only case where having two separate index helps. Uh, and the only example that I know where it works well is like this shared documents where think of like a document, you either have permission to the document or the document is public. So find all the public document, find all the document that you have permission to, and then you just union them together basically. So you can union them manually, which is dumb, or you can just do this or and like these two separate indexes, and the DB is smart enough to figure out that can internally union them. It is slower than single index, but it is much better than, you don't need to necessarily create two indexes here. Two composite indexes here. So that is one example, only edge case where it happens. Any other questions? Okay, we have 15 minutes, we'll have to go fast. Last major topic is concurrency. This is where everything you know so far, like that has to now happen in parallel with several users. So even though DB user might be one, but like your application might be firing queries simultaneously with like 10, 20, 30 users all working at the same time, background jobs doing the same thing. So we'll start with what are problems that come up when you start when you have this concurrency of different queries. The first basic question is like first basic problem is you have this problem of unrepeatable read. Now databases don't have this. Like this, I'm just explaining what are the problems that exist and how databases solve them. So first problem is unrepeatable read, where you read something and while you are doing something with it, someone else has modified what you are reading. Like if you read a user's data and that user was modifying their own data, and you read it again, now you are seeing something else now. So there is this inconsistency here where like you are reading something was 10 and then you read it again. By the time your transaction added, now you suddenly have 19. So like applications start breaking when they see this kind of mismatch because they don't know how to reconcile this. This is called unrepeatable read. Then you have this dirty read where you read something and you wrote to something. Like you updated a user's profile, but you did not commit it. But now someone else is seeing your unwritten changes. And they saw your change, but you never made the change final. Like you just aborted it. So you rolled it back, but they are still seeing the thing that you changed. So you never meant to do that change, but someone else is seeing that change. So this is called dirty read, where your uncommitted writes are visible to others. And lastly, this is lost update, where you wrote something, someone else also wrote something on top of it. You wrote something again. So like you lost, your update was lost in the while resolving concurrent transactions, and you don't even know that the changes I made were not actually final because someone else overrode my change. So all of these confusing things are avoided, have to be avoided somehow, or at least reduced so that you can write your application in sane manner. You can't resolve all these things manually because it's way too confusing, way too hard to get concurrency right. So databases kind of take all of these responsibility on themselves, and they provide these ACID properties. Have you heard ACID so far? Yes, college mein suna raha. So ACID is this is the acronym for atomicity, consistency, isolation, and durability. All relational databases pretty much provide this. They trade off a little bit of here, a little bit there, but they have to provide some version of this. Atomicity means either everything happens or nothing happens. Means think of like bank transactions. Like if I pay you 100 rupees, you have to deduct 100 from me and add 100 there. You can't fail in between. Like you have to either do it or not do it completely. So that is atomicity. Consistency means whatever I have specified to be correct, it has to stay correct. As in, if I say username has to be unique, you can't suddenly have two people with same username because if the database failed to enforce that consistency. Isolation, you have varying level of isolation. So the parallel transactions that are happening, they should be isolated from each other until they are finalized. And you decide when to make them visible to others based on your isolation level. We'll come to that. And lastly, the most important thing is if you commit something, it should stay committed. It should not like magically go away or randomly go away. The data should always be persisted. And that is very, very hard to solve. We'll see the durability part later. So for first three things, for atomicity and isolation, you have to understand how the DB solves things locking internally. So basically, databases have these two type of lock, shared lock and exclusive lock. How many of you have done any kind of concurrent programming where you have to lock things manually? One person. Okay. You should, all of you should take some operating system class, because operating system classes are very misleading. You think they are about operating systems, but they are about low-level programming, they are about concurrency, they are about all of these other things. They are named poorly. So in concurrent programming, or parallel programming, you have this read-write locks basically. So the same concept is translated here. The S lock is shared lock, which means I want to read something, but while I'm reading, please don't change what I'm reading. Because if you just change it, then whatever I'm doing will not make sense. Think of things like I'm trying to validate someone's credit score, or someone's like a balance limit. Like you cannot have more than 10,000 rupees. And while I'm trying to validate the 10,000 rupees, someone does the change while I'm validating. So that makes my application logic weak, right? So you have to put some shared lock on that thing so that it does not change while you are doing some processing. Xlog is exclusive lock. It just means you fully intend to modify it. I'm reading this and I'm also going to modify it in some time. So in that meantime, like don't let someone else modify it. Now, how many of you have manually done shared lock or Xlock in SQL queries? None of you have done? You should have, probably. What is it called?
I did it because one of the deploys.
No, how do you do it? Yeah, so what is for update? Shared lock or? It's exclusive lock, yeah. So most common lock that people use is exclusive lock. Shared lock has very few real use cases that I have seen, but still you need to know how it works. Because shared lock is more flexible. Like multiple people can have shared lock. Like multiple people can see that the account balance limit is 1,000. But if we put exclusive lock, then only you can see the limit. So exclusive lock again is the most common for update. Like putting for update at the end of the SQL query is how you lock rows, and it implies that I am selecting these rows, but I intend to update these rows. Like don't let them change while I'm doing something else. We'll see how the locking things work. And when most of you answered you don't lock, it's because in databases there is no such like the explicit locking happens very rarely where you specify I want to lock. Most of the time it is just happening for you. Like you don't even realize it is happening for you. So there's this thing called two-phase locking, where like this, think of this as like your transaction where you are reading something, you are modifying something, you are deleting something, and in the end you say, please commit everything. So while you are updating something, DB is internally putting locks where you might not even think that it is putting locks. And once you are done with your work, you have enough locks, and it will wait until you are committing, and all the locks are released automatically. So you don't manually do lock unlock at all. Like it is just happening when you say for update or when you update something or delete something. It is putting in those locks, and eventually all those locks are implicitly unlocked.
But like when you say for update and then commit,
Yeah.
that lock, like that transaction is locked.
Yeah, that for that transaction, what you said for update is locked, but you never said unlock, right? Like don't say unlock the rows. Commit is the unlock, basically. So that is why it is called two-phase locking, where like there is this growing phase where you are acquiring more and more locks, but you never unlock things here. Okay, and it is important because if you allow randomly unlocking things in between, then you run into deadlocks and all the other crazy things. So you can only lock things in SQL. There is no concept of unlocking, manually unlocking. You can unlock everything at once, or you can unlock nothing while you are doing the job. So again, I'm not fully explaining because it's like 1 hour explanation. But you can look up this term and figure out why they don't allow you to unlock things. But this people understand, right? Like there is no explicit unlock. More or less, you just keep locking things, and ultimately, when you are done, everything is unlocked. That's why it is two-phase. There is this phase where you are acquiring lock, and then there is the final phase where you are just done with the work. This is the example where even though you are not specifying it explicitly, but when you say, like this is the same example where the A is transferring 100 rupees to B, like I'm transferring 100 rupees to Aradhya, and the initial balance is we both have 1,000 rupees, and if I transfer 100 from me to him, the final A plus B should always be 2,000 because you can't magically make money out of nowhere. So here you need to make sure that this, while this is happening, no one else updates the same things. So we lock A, like I lock my balance, then I read what I have, I reduce my balance, and like I write it back. Like you can't, because in place you can't update. So you read, you deduct, you write it back. So my balance is now updated. Then I lock his account. I do the same thing. I read his balance. I add 100 to balance and I write it back. And then at the end, before committing, both are implicitly unlocked. This happens all implicitly. You don't manually do it. Now, you might be wondering why we do this read, then modify, then write, and why not just say write A minus 100? Like because update queries are just update balance, do it A minus whatever is minus 100. That no, so again, when you say update balance to be less than what it used to be, that is a declarative concept in our head. There is no such thing at like binary level where you can just say you have to read something, modify it, write it back. Like everything at low level works by read, write, read, write. So when you do it in between, you can mess it up and have some concurrent thing. So if you do it right, then whoever is reading the balance will not be able to read the balance until you have committed your balance. And then when they read it, they will read the right version of it. And if you aborted it here, both will get unlocked and it will be right. So the rollback and all those things are also very internally managed. We'll see later. But any questions about this kind of locking? Yeah, because this is shared lock, which means I want to read something, but I don't want it to change while I read it. So if someone is planning to change it, then in this process it is going to change. This is an exclusive lock, right? Like I have an exclusive lock here, so no one else can read it in shared mode also. They just want to read, they don't just want to read it. They want to read with guarantee that it won't change. So shared lock means read lock. Like I'm reading something, but I don't want it to change. Cool. Okay, so any questions about locks like this? Shared is basically read lock. Exclusive is write lock. I want to write something, you have exclusive access to it. Yeah, that is right before, as in, doesn't matter, like in you don't see it, but in the internals it will be right before, not after. Okay, the another important concept is this deadlock. How many of you have seen deadlock while using Frappe framework? Oh, plenty of people. Okay, how many of you understand how deadlocks happen? Okay, few of you. So okay, okay, some basic. I forgot one basic thing here, where if you have this read lock and write lock, do you know the compatibility? The same question you asked, like why can't I just read what is being exclusively locked? So this is the same thing that comes from OS, where like reader writer locks, where there can be multiple readers, but there can only be one writer, because if there is one writer, then readers are not guaranteed to get the right result. But if there are only exclusive, if there are people only reading the data, then all of them can read in share mode. That's why it is called in share mode. Like you can read things in share mode, but you can only exclusively write something. Because if you write and someone else is reading, they are getting the wrong picture. That was the explanation for that. Deadlocks happen when you have this kind of like circular dependency. Like this is a more complex example. This can happen with two things also. Like here the circular example is like, because this is a more complex example with three queries. Like so first A has acquired lock on A. Sorry, the transaction 1 has applied lock on A. Here is the lock exists on B. Then lock exists on C. Now this one wants lock on A. Now it can't get because this one has the lock. The first transaction has the lock. So like there is this circular dependency here, and it will never be resolved. It is impossible to resolve because this can't do the job further. This can't move ahead. So what typically happens in databases is they have this deadlock monitor, like a separate thread is running that is just seeing if there is this graph. It will just abort something so that the graph can move forward. And it has some heuristics to decide what to kill. If you look at deadlock logs, it will, in InnoDB, it will show which query it killed. And the heuristic is mostly, it decides, okay, which transaction has done more useful work, like this has done thousands of writes, this is just doing first write, so it will kill this one and not this one. Because aborting this is way more costly than the other one. Some heuristics, you can't rely on it, but mostly deadlocks are resolved by some internal thread, which decides I'll kill something so that I can resolve this circular dependency and move forward. So whoever gets killed is obviously fails and has to retry whatever they are doing. Any questions about deadlocks? Yeah.
So if there's an X lock, then no S lock can be acquired.
Yeah, Xlock is not compatible with anything else. So again, I removed the compatibility slide because it is quite complex, all of those things, and we don't have time, but yeah, this is, so I haven't covered iLock, so please ignore them. This is Xlock and this is shared lock. So Xlock is compatible with nothing. Because any kind of lock you try to acquire, exclusive means exclusive. The shared lock is compatible with just shared lock. Shared lock, and I have not covered intention locks, but Xlock, S-lock and S-locks are compatible. The intention is also compatible, but like it is not compatible with exclusive because it's the same reader-writer problem. You can have multiple readers, but you can't have, when multiple readers are reading, you can't have another writer. And when there is any writer, you can't have any other reader. No. Every read operation does not implicitly take S-lock. We'll cover that part. If you want it to be read in shared mode, you have to explicitly say for in share mode, like while locking, which we don't do mostly. For update is the most common one, but in some cases you don't need exclusive lock, you just need read lock. Okay, I'll skip this for now. Intention locks are also something you should read up on, but I don't have the time today. Intention locks are these things where everything cannot be locked at, yeah, I'll have to take 10 more minutes because if I continue afterwards, then it will take too much time. So intention locks are these things where there are some operations that require like table level things. So I'll show that example. Okay, so like think about cases where you're not modifying one row or one table, one row or like several rows, you are modifying entire table. You are saying alter this table to add this column. That means I intend to modify the entire table. I don't want a individual lock on every row. I just lock the whole table so that no one can modify it there. So to resolve this kind of operation with this, you have to have this another layer of locks, which is I intend to modify everything below. So you cannot lock this anything below. You have a question? Yeah. Okay. Okay. So intention locks are just like I intend to do something down below, and this is the hierarchy. Like there is a database, there's table, there are pages, and there are individual rows. So most of the locks we spoke about are applied here, but intention locks are applied at the top, where like I intend to modify everything below. So please don't allow anyone else to do anything else. So those are basic locks. Now these locks solve everything? Like if you just like it is the SOP season and Frappe people are here. So when the budget is tight, you typically look at who has the max salary and fire them to save budget. You don't fire, but you at least start looking at, okay, are they doing well? If they are not doing well, this is what we do, by the way. We sort by CTC when any kind of accountability happens. Okay, are you justifying your CTC or not? So it is safe to have lower CTC, but this is what happens. So you do this in your head, okay, who has the max salary? How can this go wrong? It is SOP season, people are updating the salaries and you are trying to find who has the max salary. There is no lock here as such. What will you lock here? Salary what? Like you don't want to lock entire column. You lock the max salary? It is the thing, but that is the okay. That is the answer. So uh, let's say while you are selecting, a smart ass comes. Like this used to be Aditya, but now that I have changed the name to me. I will insert new salary where my salary is 40 lakhs. This is the only joke in the entire presentation. So, so while this is while you are trying to select, if someone is inserting salary which is like higher than the maximum, like then the max you get is different than the actual max that is going to exist. So I am pretty contrived example just for the joke, but you'll find examples like this in business logic also, where you want to make sure that no one can insert something that does not exist also. So think of this as example. Where these are the salary ranges where you are trying to fire the person who is the most salary. But while you are doing that, I insert I insert my row which does never existed before. So the last row does not exist. You can't lock something that does not exist. So what MariaDB does, or allows doing at least, is we allow locking gaps. And gaps are these things that exist in between values, as in 10 and 25, there is a gap. But if it was 10 and 11, there is no gap as such, because you can't insert a number in between that, unless it was floating point. So these are all the real gaps, and then there is this infinite gap, like from 39 to infinity. Like this gap exists, and you can't insert anything. You can lock it if you want. Like don't allow anyone to insert anything here. And similarly, like this is how it looks. Like in the page metadata, you will have this kind of gap bits or something where you can say, okay, put a lock here. Don't allow anyone else to insert it. Because while you are inserting in the B tree, literally there is a gap in B tree where you are inserting some data. So you take the lock on that gap and you don't allow inserting anyone. Now, how this happens, again, I will have to do demo, and maybe we'll have to skip your talk. I'll do it later. It's okay? Do it later, as in after lunch. There's plenty of time. Cool. Is it okay or? It's okay? Yeah, chalta hai. Okay, I'll show you the demo of how this works, because this demo is important. Otherwise, it is just gyan. Okay, I'll show you a demo. So here I'm creating a new doc and just inserting like a to-do with nothing fancy going on. Okay. It got inserted. It is not committed yet, but it's just inserted. And in another console, like you can think of these console as like two different transactions. So in another transaction, I'm trying to select everything that is newer than some date, and I want to do something with it, so I want to lock them also. Like this is the exclusive lock that I'm trying to acquire. If I do it, what happened here?
So there's a log there already.
Yeah, so I'm trying to lock everything. Like basically, I'm trying to find everything greater than that, but I can't be sure because someone is inserting right now something in that gap, which is because the creation is indexed, right? And here the creation has, so on creation index, this transaction already acquired lock for that gap. Like I am inserting in this gap. If someone wants exclusive access to that gap, they can't have it. So this will wait for a while. Do we want to wait, or I can trigger the thing? So if I roll back, that means the other transaction now has go ahead to proceed. But if I did not roll back, what would have happened is like after 50 or so seconds, it would say lock wait timed out. You can't, like we waited for the lock, but we never got the lock. Yeah, either commit or rollback would have unlocked this lock, and the other transaction would have gotten a chance to go ahead. This will happen the other way around also. Like if I do this, now what do you think will happen when I insert? Not this. It won't, because all the entire range is locked. The gap is also locked beyond the infinity to infinity. So I can't insert because I'm trying to insert in that gap, and someone is modifying that gap potentially. So no. So I'm locking the documents right here. I'm saying give me everything that is greater than this. This document does not exist. So how can I lock this document? It does not exist.
So are these locks turned on by default, gap locks, or is this something?
Gap locks are turned on by default when you have repeatable read, which is default.
So this one's a gap lock, right? The one before that was
Both were cases of gap lock. Like whether you do it in this order or that order, like this is the timeout error that you get after 50 seconds. So only when you, so again, when we said index contention happens, when there are too many indexes, the contention only happens, the updating contention is one thing, but this kind of lock weight contention only happens when you have for update. So stock ledger has this problem because it has for update on certain rows. So while you select the rows with this kind of range queries, like give me something greater than this, and you say for update, you are locking the entire gap. So no one can insert new stock ledger while you are processing that stock ledger in that gap. In this case, it is infinite. It could be like less than this, greater than this, then the gap won't be infinite. Like you have to, the gaps are like very, like depend on how you have written the query. And sometimes it is also everything in between. Everything is locked. So if you say for range of this and this, like everything in between gets locked. It's not like just a gap between two numbers. Cool. So that was the demo for this. This was the question to your answer. So answer to your question where there are just varying forms of isolation levels, and you decide which isolation level you want. Like so by default, MariaDB does this thing called repeatable read, which means whatever you see once, if you query it again in the same transaction, you will get the same data back. Like even though someone has changed it, you don't see the different version. There are this weaker form of isolation where you can see if someone has already committed and you request the data again, you will see the different version. There's this serializable, which is like the strict version where everything is essentially serialized. So like there are no parallel transaction in theory. Like in practice, you can have parallel transaction, but in the backend, it will figure out a way to just serialize everything. I'll not go too much into detail here because we don't have time. Last important thing to know here is MVCC. It's called multi-version concurrency control. It's like every row where you're modifying is timestamped. So and the other person can read the same row they were reading because database internally is keeping multiple copies of the same row. And the final version get replaced when you commit it. But until you commit it, there are multiple versions of the same row inside the database. And again, the old copies get purged when no one else is reading it. So if you have, let's say, if you are updating two things, if you're updating a row and someone else is also reading the row, the old copy will still stay there until the old transaction is gone. So if I open a DB console and read something and don't close the console at all, that old version of row will stay there forever until the transaction ends. So that is why when we say you don't want long-running transactions, it's because when you start a long-running transaction, you are creating copies of everything that you are reading, and that copy cannot be deleted because you need to be presented to that version, older version. And I can't do the demo, but let's explain the rationale behind it. So when you do MySQL dump, like you are backing up the entire table, you are telling me that you're telling the database like give me consistent version of database at this point, which means database has to keep copy of everything at that point until the backup succeeds. So if backup takes 2 hours, for 2 hours it has created copy of everything that was present at that point and that is being modified by someone else. So that is why long-running backups slow things down, not necessarily the I/O and all of this, but like you internally have to manage so many copies here. Same thing with long-running updates, long-running queries, long-running transactions. All of them cause this problem. So by optimizing the time, you are indirectly optimizing a lot of other things like request time. I'll skip this part because it's not so important. Last important bit is logging and recovery. Since we are taking up this slot, we'll have 10 minutes. So deadlocks are solved by serializing the order of acquiring locks. As in, you make sure that if you have two transactions, one is updating a document, another is processing the document in background, you make sure that you acquire the locks in same order. Because if you, like here the problem is, here the A is acquired first and then the B is acquired. Here the C is acquired first and A is acquired second. If we just flip this order, like this will wait here instead of creating a deadlock. So the basic solution to deadlocks is always acquire the lock in the same manner, but you need to know what locks you are acquiring, and SQL doesn't tell you directly. You need to figure out like where you are internally, where you are doing for update and which document you are trying to lock, and you need to lock them in same order. That is one solution to like completely eliminate deadlock. If you acquire them in same order. The other more practical thing is whatever you are doing, if it is too slow, just try to make it faster, so that there won't be these overlaps where you are trying to acquire locks in parallel and which have this circular dependency.
But with a lot of component users, wouldn't you get a lot of deadlocks?
You would, but let's say if the thing is fast, like if thing is executing in millisecond, then the deadlock chances are reduced because your overlap is much smaller. Like the larger the overlap you have, like if you have a transaction running for 10 minutes, you are way more likely to get deadlocks because you just have this long running transaction that has locks and someone else can come and cause a invalid lock. So that is just a way to, making things faster or making transactions smaller is just a way to reduce the likelihood of deadlock. It does not eliminate. Elimination, the only way is you identify where you are deadlocking and you make them sequential. Like you always acquire lock in A, B, C, D. So there is no way of going, like building this dependency in the first place. So think of it like this way, like you first acquire lock on database, then table, then row. If you are doing this in arbitrary order, then there is a likelihood that you. Okay, so the last topic is logging and recovery. This is very short topic, so if you have questions, you can we can have the global questions later also. Logging and recovery is just like when I said durability is important. When you commit something, it should be committed, and like whatever happens, power failure, any kind of failure, not disk failure, because if disk fails, you you don't have the data, but everything else should be recoverable by default. Or if the process crashes, or you say like kill 9 the whole server, it should still be somehow recoverable to whatever was committed state. And to achieve that, we'll have to again revisit buffer pool. So this is when we discuss buffer pool, we mostly focus on how to read things, bring it to memory, read it, throw it back to disk. Now, when you are modifying something, like you modifying one row, you want to update the page and then you want to flush the page eventually to disk, right? Like for persistence. Now, this makes no sense if you are like imagine 4 KB page you are reading or 16 KB page you are reading, and you are updating one thing. You are disabling a user enable change from 0 to 1, like 1 byte or 1 byte of data that changed. You don't want to write 16 KB back to disk. So databases do not actually commit the whole thing. What they actually end up committing is writing a log of what they have done, which is faster to commit. Like you just say I changed enabled from 0 to 1 or 1 to 0 and just write that thing, and that is very fast to write because it's just small description of what you have done. And this is called write ahead log. You don't want to flush everything, you just flush the changes so that you have a better performance there. And these are things, so now if you want durability, you just need to ensure that whatever log you have done, you just commit that log into database in the disk, and then it's highly unlikely that you can't recover it from forever. So now this also has to be merged at some point, right? Like you can't just have logs somewhere and actual data somewhere else. Like then you will be reconciling both of them a lot. So what happens is there is this process called checkpointing where you pause everything, or you try to pause everything, and you read the log and try to apply it to the actual data, and then flush it to disk. So now you have accumulated enough changes. Like the same page has so many changes, you can write it to disk without wasting a write. Like doing it for 1 byte is expensive, but if you have so many writes, you can put it to disk now. And once you have done that, you can say the wall has now moved forward, like the write ahead log has now moved forward, and you can discard the log. This is similar to binary log, but it is not binary log. There is also binary log, which you might have heard, which is a more commonly used thing. Write ahead log is something different. It's very similar, but not the same thing. Because write ahead log is continuously truncated when it is merged with the actual thing. And these two have this, you'll find, like when you have too many busy writes and your write ahead log is not able to keep up, you will find this in monitoring stats where you'll see that the wall is growing too fast and not able to recover like not able to checkpoint. So these are things you will hit when you get a high throughput problems. So like just few discussion, like is it safe to kill MySQL? 99% of the time, yes. I don't know if you have ever faced problem by kill lining MySQL. You can kill it. It will, whatever was committed would have been committed. Whatever is not committed will not be committed. It will restart and it will just replay the write ahead log and apply the changes that were not flushed. I'll not show the data here. It's just too much. It's going to take too much time. What? I want the actual file, not the. I'm just trying to find the conf and show some. Anyway, in meantime, do any of you have any questions regarding this? Yeah.
So the checkpointing thing, can you just keep delaying the checkpoint?
You can, but then your recovery time, like if it gets killed in between, while recovering, you will have to apply replay all the write ahead log on top of the older buffer pool.
No, so like if you're sure nothing is going to go wrong, and can you just keep delaying the checkpointing so that you don't know?
You can technically, yeah, because the buffer pool will have the applied change in memory. It will not be flushed to disk. So if you keep delaying it, when it crashes or when it restarts, it will have, or when you request like a graceful shutdown, it will have to apply all of the changes to flush to disk. So you can do it, but it is not a good idea. So that's why we have some limit on how much the log should be. Like it would be few megabytes. If I can open this, okay. So this is the log file size. I think this is the write ahead log size. I'm not 100% sure, but like this 512 megabytes. So you keep logging every change, and when that size hits 512 megabyte, it will stop and try to flush it. It also does it periodically before that it hits that limit also, but this is like a hard limit beyond which it will not allow you to do it. Like it will try to pause as many things it can and flush it. And this is about durability, which means like there are different numbers here that basically means like you definitely should flush the log to disk, because if you don't have this, then you'll have better performance because you're not hitting disk, but you'll also have much higher risk of losing some data when losing like 1 second of writes, not so much. That's about it. The recurring question is, how do I learn to index things? Read this. There isn't much science to it. There is this website called Use the Index Luke. Again, people will not get the Star Wars reference. But yeah, this site is pretty good. You can learn how to read queries and figure out which are possible indexes and how to index things. It's not worth covering it here right now. Any queries so far, or feedback just on how to do this better? Questions? As far as I know, no. It will do like you do. So think of it this way: like you have millions of frames in your memory in your buffer pool. When it flushes, like you need to make sure that if I'm flushing like 10 logs, these 10 logs belong to these 10 pages. So you have to flush those 10 pages to disk and then discard this log. So you can do little bit of locking, little bit of flushing, little bit of locking, little bit of flushing. This is how I picture it. I have not seen the actual implementation, but you don't need to lock everything to flush it. But lock at least what you are trying to flush.
So, no, when you said like a lock, I immediately imagine as a Python library.
No global lock, no. There are very few things that require global lock, because by design it would be pretty stupid to have global locks. Then you will see this latency spikes whenever those operations happen.